Ionic bonding. Right, so first the definition of ionic bonding. An ionic bond is an electrostatic attraction between oppositely charged ions. Electrostatic attraction between oppositely charged ions. So static just means it doesn't move. Yeah, it's charged but it doesn't move. Okay, now that's the definition of an ionic bond. And an ionic bond is normally between a metal and a non-metal. So it occurs whether you've got a metal and a non-metal. Okay, so for classic examples are things like sodium chloride, metal, non-metal, magnesium oxide, metal, non-metal, things like sodium hydroxide, okay, is an ionic bond between the sodium and the hydroxide, even though there is a covalent bond between the oxygen and the hydrogen. Between the sodium and the hydroxide there is an ionic bond. Okay, so the definition: electrostatic attraction between oppositely charged ions, and it's between a metal and a non-metal. Okay, let's just take some classic simple examples. If we take sodium chloride, okay, sodium atom, well, let's take a sodium atom and a chlorine atom first. Okay, so sodium atom has got 11 electrons, so that is 2, 8, 1 for the GCSE style electron structure. But chlorine has got 17 electrons, so chlorine is 2, 8, and then 17 electrons in GCSE style. Okay, so what happens is the outer electrons, remember everything, when all atoms react, they want to have a full shell of electrons. They want to be like group 0, noble gas. So the outer electron from sodium is given to the outer shell of chlorine. So then you are left with, let me just remember that we've got, I'm going to write at the top here because this will help us. And sodium has got 11 protons and 11 electrons, whereas chlorine has got 17 protons and 17 electrons. Okay, so now it is no longer an atom. Okay, because now if we give one electron away, we still have 11 protons, but this time we've given an electron away, we only have 10 electrons. So 11 positive and 10 negative gives you an overall charge of +1. So now we've got a sodium ion and it's got a full outer shell, 2, 8. Okay, and if we go over here with chlorine has still got 17 protons in its nucleus, but it's now got an extra electron from sodium, so it's got 18 electrons. So it's got, if you put them together, that's going to give an overall charge of -1. It's got 1 extra electron. So this is now an ion. So that's an ion. It's a charged atom. That's an ion, and it's got the electronic configuration 2, 8, 8. Okay. Now you need to be able to draw a dot and cross diagram. Just going to this paper. Squeeze it. Let's squeeze it on the bottom. You need to be able to draw a dot and cross diagram. Okay, it's called a dot and cross diagram to represent the ionic bonding in sodium chloride. Okay, in sodium chloride. So if we have the sodium, okay, and we always represent the outer shell. We don't represent the inner, we just represent the outer shell. So there is no, the third shell isn't there anymore. we put square brackets. You have to put square brackets because square brackets represents an ion, which means an ion. And we have a positive charge. So there are now no electrons in the outer shell, so we don't represent anything. Whereas with Cl has got 7 of its own, so 7 dots. Remember, they go around in pairs. 7 dots. Okay, so 7 outer electrons, and it's got an electron from sodium, so it's got a cross, and then it's got an overall, the Cl has got an overall charge of minus, and that is called a, remember that's called a chloride ion, not a chlorine, but a chloride ion. And that's the dot and cross diagram for sodium chloride. So the dots, it doesn't matter whether you choose dots or crosses for chlorine, and then a bonus electron for from sodium. Okay, let's try another example to represent for an ionic bond. Okay, let's do magnesium oxide. Magnesium oxide. So let's build it up. Magnesium has got 12 electrons. Okay, so it's got 12 protons and 12 electrons as magnesium. So magnesium is 282 in GCSE style electronic structure. Okay, oxygen has got eight protons and 8 electrons, and that is 26 in GCSE style. Okay, to have a full shell of electrons, the 2 outer electrons here need to be transferred to the oxygen, to be given to the oxygen. Okay, so when that happens, when 2 electrons are given, that means magnesium now still has 12 protons, but it's lost 2 electrons. So now it's down to 10 electrons. And so that gives an overall charge, 12 plus and 10 minus is therefore plus 2. Now, oxygen has still got 8 protons, but now it's got an extra 2 electrons to have a full shell, and that is now 10 electrons, so it has an overall charge of minus 2. Okay, so when you draw the dot and cross diagram, magnesium is the metal. Remember, metals lose electrons. Magnesium is the metal. Its outer shell is now empty. It's got a positive charge 2 plus. And now the oxygen is an ion. Remember, we're using square brackets for ions. And the oxygen. Now, oxygen has 6 of its own electrons. 2, 4. Now, you've got to be really careful here. 5, 6. It only pairs up when it has to. So you've got to put them singly like that, the 2 electrons in oxygen. Then we have an electron from magnesium pairing up and an electron from magnesium. And together that gives an overall charge of 2 minus. And that's the dot and cross diagram for magnesium oxide. Okay, so that's the bonding in ionic compounds, the bonding. So what is the structure? Okay, so the structure, so when you say a bond, that just means what's going on between two items, a bond. The structure looks at lots of ions, yeah? It's not just, if you take sodium chloride, for example, if you take sodium chloride, that is not just one sodium ion and one chloride ion. That is lots of sodium and chloride ions together, okay? So what you get is the way it's packed together, and opposite charges are next to each other. So a sodium ion will be next to a chloride ion, and like that, and its opposites are next to each other, okay? Opposite ions, and each sodium ion is surrounded by, each sodium ion is surrounded by 6 chloride ions, and the opposite as well. Each chloride ion is surrounded by 6 sodium ions. Okay, so it's a giant structure. And the way you draw it with opposites, you draw it and it's a cube. For sodium chloride, it's a cube. So you've got to draw a cube. Because it's not just one single sodium ion and a chloride ion, it's a cubic structure. Okay, so you'll have a sodium ion, okay, then you'll have a chloride ion, and then you'll have a sodium ion, and then you'll have a chloride ion, and then you'll have a chloride ion, and a sodium ion, and a chloride ion, and it's a cubic structure. Okay, actually it might be better not to draw it that way. Let me do that again, because it actually might be better to put more ions in. Let's do it one more time. Let's just put some more ions in. So draw a cube again and draw the back of the cube. Okay, it might actually be clearer if we put a sodium ion and then to the middle put a chloride ion, then a sodium ion, and then in the middle put a chloride ion, then a sodium ion in the middle, and then a chloride ion, and then a sodium ion, and then a chloride ion, and then a sodium ion, and then at the back will be chloride ion, and then a sodium ion, and then in the middle chloride ion, and then a sodium ion, and then chloride ion, and a sodium ion in the middle, etc. Right? But it's a cubic structure, and there's a very good picture. If you look in a textbook, there's a very good picture. All right? So it's a giant. So the name of the structure. So bond is what goes on between just two atoms. The structure is when you've got lots, and it's the way it's packed together. And this is called a giant ionic structure, or the word lattice. Now the word lattice just means a regular pattern. So it's just a regular pattern, like lattice fencing, for example. Or lattice apple pie, when you put it on top of an apple pie. So it's a giant ionic lattice is a structure. Okay, nearly finished. We need to talk about the properties of ionic compounds. So the properties of ionic compounds. So there's three properties we need to look at. So the first property, this is the properties of ionic compounds. Properties of ionic compounds. So the first property is that ionic compounds like sodium chloride, like magnesium oxide, have got high melting and boiling points. Now they are solids. So first you've got to melt them and then boil them. And the reason why they've got high melting and boiling points is because a lot of energy is needed. A lot of energy is needed to overcome the strong electrostatic attraction between oppositely charged ions. Okay, so the marking points there are, we've got high melting boiling points because a lot of energy is needed to overcome the strong electrostatic attraction between oppositely charged ions. Yeah, and the higher the charge, the higher the melting point. Yeah, so the higher the ionic charge, then the higher the melting point. I'll give you a couple of examples there. So if you take, for example, let's take that one. If you take sodium fluoride, okay, with that, it's got sodium ions and fluoride ions, then that has a melting point of 993 degrees, the melting point. Okay, but if you take something like calcium oxide, which has got a 2+ charge and a 2- charge, that has a melting point of 2614 degrees, 2614 degrees. You don't have to remember specific numbers, but you do need to realize that the higher the charge, the higher the melting point. And also the size of the ion is important. A small ions can pack closer together. Okay, so that's melting point. That's one of the properties, melting points, yeah? The second property of ionic compounds is electrical conductivity. Okay, solid ionic compounds cannot conduct electricity. Cannot conduct electricity. Okay, that is because the ions cannot move. They are fixed in position, right? So if you look at the drawing we drew moments ago, okay, the ions are in a solid lattice, okay? They cannot conduct electricity because the ions cannot move. They are fixed in position. And the ions, they sometimes use the term mobile charge carriers. When you're conducting electricity, you need something to carry the charge. So the ions, sometimes we use their mobile charge carriers. There aren't any mobile charge carriers. There's no ions that can move, okay? So it cannot conduct electricity. But when you dissolve in water, the ionic compound, the ions can now move. The ions are free to move and conduct electricity. Also, as well as dissolving in water, if you melt this ionic solid, again the ions are free to move as well. Okay, so that's electrical conductivity, and the last property is solubility. Solubility. Okay, so there's three properties. The last one is solubility. Right, is it soluble? Yeah. So most ionic compounds are soluble in water. Most ionic compounds are soluble in water. Okay, and that is because water is a polar solvent and can break down the ionic attractions. Okay, now when you dissolve, when a solid dissolves, there's two things happening. When a solid dissolves, there's two things happening. Okay, so first, the ionic lattice has to be broken down. That's the first thing that happens. Yeah? Okay, so the first thing that happens is the ionic lattice, let's take sodium chloride, has to be broken down into ions. And then the second thing that happens is the water molecules are attracted and surround the ions. Okay, for example, if you take sodium ions, the negative end of the water molecule, right, we've not done this yet, but soon there's a negative end to the water molecule. Okay, what I'm drawing there is it's called delta. It's called delta. It's a symbol, and it means slightly. In chemistry, it means slightly. We'll do that when we do it comes under the topic electronegativity. Okay, so the water molecules surround the ion like that, etc. Whereas a chloride ion, it's the other end of the water molecule that surrounds. But we'll do more of that next time, yeah? But the problem as well is, if the ionic compound has a large charge, so if the ionic compound has large charges, then the solubility decreases, yeah? The ionic attraction The ionic attraction is too strong for the water to break down, for the water molecules to break it down the lattice. Okay, so it's not soluble. So if you have an ionic compound with large charges, then it is not as soluble, right? So for example, let me give you an example. So we've got, if you take sodium chloride, okay, which has got sodium ions and chloride ions, its solubility is 6.1 moles for every 1 decimeter cubed per decimeter cubed, yeah? Whereas if you take calcium carbonate, which has got 2 plus ions and 2 minus ions, its solubility is 1.3 times 10 to the minus 4 moles per decimeter cubed. All right, remember 1.3 times 10 to the minus 4 is like that. 1, 2, 3, 4, 0.000 moles per decimeter cubed. So it's less soluble because it's higher charge and the water molecules cannot break down the lattice, okay, because the ionic attraction is too strong.